In this video, we'll move to the second step of our sequential multiple regression example, starting to work our way through the causal sequential model. We initially mapped out how we believed our three predictors, mother's education, school quality, and study hours, influenced our outcome grades, and how they influenced each other as well. We started in Model 1 with the first variable in that causal sequence, mother's education, as our only predictor. We're now going to add the second variable in that causal sequence, school quality, as an additional predictor in Model 2. So let's start by looking at the ANOVA table after we've added school quality. Okay? Here we see that mother's education and school quality as a set or team has a statistically significant effect on grades, with an F with 2 and 397 degrees of freedom equal to 32.685 and a p-value less than 0.001. Now, how large is that combined effect? Well, let's look at this model summary table. And in it, we see that mom's education and school quality as a set account for 14.1% of the variance in grades. The inclusion of school quality accounts for an additional 1.4% of the variance in grades, which is statistically significant, with an F for the change in R squared with 1 and 397 degrees of freedom equal to 6.331 and a p-value equal to 0.012. This F for the change in R squared is the test of whether school quality accounts for any additional variance in grades beyond the effect that we saw for mother's education. Or maybe its additional contribution is just 0. Now, given that our F-test is statistically significant, it suggests that the unique effect of school quality is not equal to 0. It's not just random noise. It seems to be real. Great. Now, the formula for the F-test for that change in R squared is the R squared new, the R squared for our current model, minus the R squared old, the R squared for our previous model, divided by K new, the number of variables in our current model, minus K old, the number of variables in our previous model. All of that divided by 1 minus the R squared for our current model over N minus K new, the number of variables in our current model, minus 1. If we plug in the numbers, we get our F change in R squared is equal to 0.141 minus 0.128 divided by 2 minus 1, all of that over 1 minus 0.141 divided by 400 minus 2 minus 1, or 6.331. The degrees of freedom for our F-test are the K new, then again the number of variables in our current model, minus K old, the number of variables from our previous model. You can think of that like the degrees of freedom for the change in our regression model. So it's 2 minus 1, or 1. Our second degrees of freedom is the same as the degrees of freedom residual from the overall F-test in the ANOVA table. It's n minus the number of variables in our current model, minus 1, or 400 minus 2 minus 1, which gives us 397. Now, we need to remember that degrees of freedom residual, again, because we'll be using it with the t-test for our regression coefficients. So let's write out our F-test as the F for the change in R squared with 1 and 397 degrees of freedom. Remember that those degrees of freedom equals 6.331 with a p-value of 0.012. And remember, this is the F-test for the change in the R squared, not the F-test for the overall model. They're two different things addressing two different questions. Now, this 0.014, that change in R-squared when we entered school quality, is the total effect for school quality. It's the effect controlling for preceding variables and any common causes like mother's education, and before we've added any subsequent variables. We can see that with a Venn diagram. When we look at this change in the variance accounted for with a Venn diagram, things get interesting. Here are both mother's education and school quality as predictors of grades. In Model 1, we only had mother's education with an R-squared of 0.128, or 12.8% of the variance in grades was related to mother's education. And now we've added school quality, which increases that R-squared by 0.014, or 1.4%. Mathematically, we see that the R-squared for grades predicted by mother's education and school quality equals the R-squared for grades based only on mother's education plus the change in R-squared when we added school quality. This solves to 0.141 equals 0.128 plus 0.014, again within rounding for those numbers. Now, notice how from a variance perspective, sequential multiple regression addresses that who gets credit for C problem. And by C, again, remember, I mean that outcome variance that's shared by both mother's education and school quality. Remember, in simultaneous multiple regression, neither predictor gets credit for that part of the variance. Sure, it's included in the total R-squared, but if you look at the effect for individual variables, simultaneous multiple regression only considers their unique variance after removing the effect of the other variables. In sequential multiple regression, our model determines who gets credit for that variance shared by multiple predictors. Our model says that mother's education influences or causes school quality. And so any variance they share, they overlap, is due to mother's education. It's not some vague correlation where we don't know which is influencing what. Our model says it's due to mom. So that variance, that C variance, belongs to mom. And in sequential multiple regression, she's not stuck getting credit for some potentially measly little unique effect. No, she gets the full 0.128 because she is the driving force behind that effect. Consequently, as we previously noted, the cumulative change in variance accounted for at each step of the analysis reflects the total effect of each variable. The 0.128 when we added mother's education was the total effect for mother's education. And now that 0.014 for school quality, after mom gets her due, is the total effect for school quality. Okay? Now, with that, let's stop here for now. In our next video, we'll finish our examination of Model 2, starting with the coefficients table. Okay? See you then.